వచ్చింది లేదు సార్.
ఓకే
సార్ లైవ్ స్టార్ట్ అయింది సార్, కంటిన్యూ చేయండి.
ఓకే. హాయ్ స్టూడెంట్స్, గుడ్ మార్నింగ్. వెల్కమ్ టు గోవిద్య. In continuation to the previous session, we are going to solve some more questions related to the electrical transformers. Okay, so the given question is about in a 50 kVA single phase transformer, the iron loss is 500 watt and full load copper loss is 800 watt. The efficiency of the transformer at full load at 0.8 power factor lagging is. Okay, so I already told the approach how to solve the different questions. Okay, just look after it. Concept is, what is the concept they are asking? Efficiency of the transformer. What is the formula? We know the formula related to calculation of efficiency of transformer is, you can write from simple output by input. Any efficiency we are going to calculate by output power by input power. Okay, since it is a percentage, you need to take into 100. So in a transformer, the output voltage is E2 I2 cos pi 2. Since we don't know about the input, so we are converting input as output plus losses. Output plus losses. That means output is E2 I2 cos pi 2 plus copper losses plus iron losses. This is the formula for the calculation of the efficiency of transformer. Okay, so the given data, we will write it. What is the given data? It is a 50 kVA transformer. The kVA they given as 50. Iron losses Pi is given as 500 watt. Copper losses Pc is given as 800 watts. And power factor is given as 0.8 lagging. Okay, let's substitute the given data into our formula, then you can calculate the efficiency. That is that E2 I2, this E2 I2 directly can substitute as kVA. That means 50 into 10 cube into 0.8 divided by 50 into 10 cube to 0.8 plus copper loss 800, iron loss 500. Let's do the calculation. Please tell me the value of what is the efficiency you are getting, percentage efficiency. After doing calculation, you may get around 96.85% as efficiency. Okay, is it clear? Hopefully, I think it is clear for all. So in this question, where we need to be more focused. Okay, so if by looking the question, it is very simple, but the thing is, so the given kVA is in the given kVA is 50 kVA. So our formula is E to 8. That means voltage into current. So we need to convert this 50 kVA into VA. Okay, we have to substitute it as a VA. That means 50 into 10 cube. This is the first thing we need to focus. Second thing is, so we need to identify the losses. That means which loss, iron loss and copper loss already it's there, no issue. So calculation mistake. Most of the times we are going to do the calculation mistake. Second thing we need to focus is calculations. Okay, the concept is simple, formula also simple, but where we need to more focused is first thing the given data, second thing is calculation. If you are good in that, you can easily solve this question. Okay, let's move to the next question. The next question is about in a core type furnace the secondary winding is. Okay, so what they are asking, core type furnace. So in general we know that furnace is nothing but it is a heat generating equipment. Okay, heat generating equipment. Furnace is nothing but heat generating equipment. As we know, the electrical energy used for generation of heat is I square into R into T. So in order to generate high temperature, we need high current. Okay, as the heat energy is directly proportional to I square RT, in order to generate high temperature we need high current. Okay, so this is our first requirement of our furnace. Okay, so they are asking, if you see the options, they are asking about the tons. How about the secondary winding turns of a core type transformer? So if you see, we know the current. We know the current, and we need to calculate. We need to design the number of turns based on the current. Okay. In a transformer, what we need to understand, in a transformer, whatever input kVA is there, output kVA will be the almost same. Okay, so in general input kVA equal to output kVA. So the thing is, kVA is nothing but V1 I1, output kVA is nothing but V2 I2. Okay, so we are talking about the secondary turns. Okay, we need high current, that means I2 need to be very high. If I2 is high, in order to maintain constant kVA, V2 need to be less. Okay, understood? So as V2 is less, the number of turns in the secondary side also need to be less. Why? Because that induced EMF is directly proportional to the number of turns. Okay, clear? So our option is about less number of secondary turns. Clear? It is a very simple concept. If you know what is the meaning of furnace, then you can answer the question very easily. So whatever may be the theory questions they are given, we need to go from the basics. If you are strong at basics, definitely you can easily solve this question. I hope it's clear. If you have any doubt, please chat over the comment box. Okay, we'll move on to the next question. The next question is about a 220 by 12 volt transformer has an EMF per turn is 1 volt. The number of turns on secondary would be. Okay, so first of all we see the given data. What is the given data? Here it is about secondary side. If we see one center, that means 0 voltage also there. So whenever this type of rating given, means it is a center tap transformer. We might have studied in our rectifier circuit. Okay, rectifier circuit, the center tap transformer will look like this. The secondary winding is going to be splitted into two windings. At center it will be 0 volt, here will be minus 12 volts, here will be plus 12 volts, like this. Okay, this load will going to connect like this. You might have studied in the rectifier circuits. Okay, so this is the center tap transformer circuit. So what they are telling, EMF per turn they given as 1 volt. So the given data is EMF per turn is given as 1 volt. The number of turns on secondary, what they are asking, number of turns in secondary side. Number of turns in secondary side. If you see the secondary side, the circuit will be like this. Okay, so it is having two windings. So for each winding the voltage is around 12 volts. Here 12 volts, here also 12 volts. So in given data, the EMF per turn is 1 volt. Then for production of 12 volts we need 12 number of turns per one winding, and another 12 volts 12 more turns required. Okay, so as two windings are there in secondary, we need 12 turns plus 12 turns. The total turns in secondary side is going to be 24 turns. Okay, if you see the options, 24 is there, but as you need to see that options are confusing, little bit confusing. If you see C and D options, they given no center tap and with center tap. So our option will be the with center tap. In the given data itself, we identified that it is a center tap transformer, and we are going to calculate the number of turns based on that. Okay, so our option will be 24 turns with center tap. Is it clear? If you have any doubt, please chat over the comment box. We will discuss. Hope it is clear. We will go to the next question. The next question is about an ideal transformer has N1 is equal to 100 tons and N2 is equal to 200 tons with a mutual flux of pi mt is equal to minus 0.05 into t square minus 2t. The induced EMF of secondary in volts. Rahul, which question you are asking? The previous question? Rahul. You are asking about center tap question. Please type clearly. Center tap transformer question you are asking. Pavan Kumar. Okay. So in the given okay Rahul, I am going to explain again for you. So in the given data, if you see, it is mentioned as 220 volts slash 12 volt. That means by seeing this, the given data or rating of this transformer, it is a center tap transformer. We already drawn here 12 the center tap transformer circuit is like this. Okay, so what they are asking, the number of turns in the secondary side. Okay, how we are going to calculate the turns? Based on the EMF. That means if you know the EMF, as EMF is directly proportional to the number of turns, we can calculate directly from the EMF. Okay, as the given, for generation of 1 volt we need 1 turn. For 12 volts we need 12 turns. Here two windings are there. That means two parts of windings are there. So two parts of windings are there. So our required total number of turns will be 12 plus 12. So it is going to be 24 turns. Is it clear? Rahul and Pavan, is it clear? Okay, thank you Rahul. Thank you Pavan. We'll move on to the next question. Okay, the next question is about an ideal transformer has N1 is equal to 100 tons and N2 is equal to 200 tons with a mutual flux of pi mt. The induced EMF of secondary in volts is. Okay, as I told, our way of approach should need to be first identify the concept or on which concept the question came. Okay, so the question is about calculation of EMF. Okay, so we are having multiple formulas in a transformer. That means for calculation of EMF, but based on the given data, which is suitable formula we need to identify. Our concept is calculation of EMF. What are the formulas we know? As per the given data, the formula induced EMF E is equal to minus n d pi by dt. Okay, this is one formula. Another is E is equal to 4.44 pi ft. Okay, but as per the given data, the suitable formula is first one. Okay, so next given data we will note down. What is the given data? N1 they given, N1 is equal to 100 tons, N2 is equal to 200 tons, and mutual flux is given as pi m of t is equal to minus 0.05 t square minus 2t. Okay, so in a question what they are asking, that means either primary side or secondary side they are asking, that we need to be very clear about that. They are telling EMF of secondary side. So EMF of secondary side means we are going to calculate the E2. So we need to consider the tons of secondary tons. Okay. Okay, secondary side tons we need to consider d pi by dt. Okay, d pi by dt. So what are the number of tons on secondary side? 200. D by dt of what is the pi given? Minus 0.05 t square minus 2t. Okay, so by doing the differentiation, what we will get? T square differentiation will get as 2t, 2t differentiation you are going to get as 2. Okay, 200 into, if you take 2 as common, it is going to be 0.1 into t minus 1. Okay, so from after by multiplying these two terms we will get it as minus 20 into t minus 1. So our secondary EMF E2 is equal to minus 20 into t minus 1. So our option will be D. Is it clear? So in this question where we need to focus is the formula. That means we are having calculation of EMF, two formulas are there. Which one we need to choose? Based on the given data we need to select. As per given data the number of tons and flux is there, so we went to the, there is no information about this frequency and all, that's why we went to the first formula. Okay, second thing where we need to focus is the given data. In the question what they are asking is secondary side EMF. That means in substitution which tons we need to substitute, either N1 or N2. Okay, based on the question that they are asking about secondary EMF, so we need to substitute N2 here. Okay, just little care if you take, we can solve the question very easily. Hopefully it is clear. If you have any doubt, please chat over the comment box. Okay, we will move on to the next question. The next question is about the following is the apparent disadvantage of auto transformer as compared to two winding transformer. Okay, so they are asking about comparison. First of all we need to identify the concept. Our approach is first identify the concept. On which concept they are asking. The concept is auto transformer. Okay, so what are the some 4 to 5 standard points are there in comparison table. This we need to remember always. Most of the times the auto transformer conceptual questions will come from this comparison statement. Okay, I think Fani Krishna answered as C. Yeah, it is correct. We will come to that. Okay, comparison of auto transformer versus two winding transformer. Okay, based on the given options we will see one by one. What are the given options? First is power rating. We'll compare the power rating. In auto transformer, the power rating of auto transformer is auto transformer equal to the 1 minus k times of 2 winding transformers. You might have studied in your theory classes, so I am not going in depth into that, where k is the percentage of tapping. Clear? Okay, so this is about power rating. So this is the first comparison we are having. What is the option given? Power rating is greater. So yeah, from this we can conclude that power rating of auto transformer is greater than the two winding transformer. That first option is satisfying, but this is advantage only. They are asking about disadvantage. Second thing is efficiency, percentage efficiency. Okay, see, in order to get high efficiency, we need to be design our equipment for low losses. The losses should need to be less, then only we'll get the high efficiency. Coming to the percentage copper losses in auto transformer equal to 1 minus k times of 2 winding transformer. 1 minus k times of 2 winding transformer. Similarly, here k is percentage tapping. Okay. Next thing is, if losses are, by seeing that we can come to know that copper losses are less, so efficiency will be definitely going to be high for auto transformer. It is also going to be advantage only. Okay, next comparison is conductive isolation is not present. As we know that the auto transformer is designed such that the same winding will act as both primary and secondary. Okay, that means the same winding is going to be act as both primary and secondary. There is no isolation between the windings. In two winding transformer, if you see, the two windings are going to be separated or isolated electrically, but connected magnetically. Okay, so isolation is there. For suppose if any insulation failure, something happen, this may not reflect in the primary side, but in auto transformer, if any fault occurred in secondary, that will reflect in primary also. So the conductive isolation is main disadvantage of the auto transformer. So our option will be C. We will look after D option also. What is they are asking? Voltage regulation. So we know that percentage voltage drop in auto transformer is 1 minus k times of 2 winding transformer. Okay, so voltage drop is very less. So voltage drop less means percentage voltage regulation will be good. If voltage drop is less, regulation will be good. Okay, so it is going to be advantage only. So in the 4 options, only one drawback we are facing with auto transformer is conductive isolation is not present. Okay, all 3 are advantages only. So what my sincere suggestion is, especially if you are attempting any question related to auto transformer, you need to remember some standard 4 to 5 points are there. That means power rating, saving of copper and copper losses, voltage drop, like that. 5 to 6 points or standard points are there. We need to remember. Most of the theory questions will come from this only. Okay, is it clear? Any doubt? I hope everybody is understand. We'll move on to the next question. Okay, The next question is given as a 230 by 2300 volt star delta 3-phase transformer is rated at 230 kVA. Okay. Okay, Rahul, thank you. Okay, Pavan, thank you. Okay. Its rated secondary current per phase is, okay, what concept. First we will start our approach. What is the concept? 3-phase transformer. The question is about 3-phase transformer. So what the first thing we need to remember in any electrical problem is whatever may be the given data or nameplate details. Normally this will called as nameplate details. All nameplate details in 3-phase system, especially 3-phase system, are line parameters. Okay, this is the first thing we need to understand. Okay, so let's write the given data. Sorry. The given data is 230 by 2300 volt transformer they given. kVA is given as 230. What they are asking? Rated secondary current. Okay, if you see the type of connection here, they given as delta connection. They are asking rated secondary current per phase. So what they are asking, what we need to find out? Secondary side phase current we need to find out. Okay, so I already told the kVA will be same both primary side and secondary side of the transformer. So I will do the calculation in secondary side. In three phase kVA we are going to calculate as √3 VL IL. The kVA for 3 phase is √3 VL IL. Okay, so from this we can calculate as IL equal to kVA divided by √3 VL. What is the kVA? 230 into 10 cube divided by √3 into V2 is 2300. Okay. How much we will get after calculation? Sorry, the IL will get it as 100 by √3, but this is the line current. We know that in a delta system, this is the line current IL, this is the phase current IPH. Okay, what is the relation between those two? In general, phase current in delta system, phase current is equal to IL by √3. Okay, so what we got here, IL is 100 by √3 into 1 by √3. If you do that, we will get 100 by 3. The option will be 30.33 amps. The option is going to be D. Yes, funny, it's correct, 33.33 amps. Sorry, options. Our option will be A. Our option will be 33.33 amps. Our option will be A. Okay, if you look into the question, where we need to focus is First thing is the given parameters. The given parameters always will be the line parameters. Second thing is type of connection, star and delta. Okay, in delta system, what is the relation between the phase voltage and phase voltage and line voltage, and phase current and line current. Okay, if you understand these two, these are the basics from the networks. If you are good at basics, definitely you can solve the question very easily. Okay, so the finding terms need to be observed carefully. What they are asked is secondary current per phase they are asking. If it is a secondary current, just secondary current if they ask, if they not mention any phase, then you have to write, we need to write, our answer will be IL. Okay. So we need to read, only my sincere suggestion is we need to read out the question very carefully and write down each item, whatever mentioned in the question, write down each item in detail. Then you can easily solve the question. Okay. Is it clear? We'll move on to the next question. The next question is about if a transformer core has air gaps, then. Okay, if a transformer core has air gaps, then. We already you might have studied in construction of transformer. The transformer core is laminated one. Okay, the transformer core is laminated core. Transformer core is laminated and going to be staggered at both ends. Okay, so what is the question? This question is about the construction of transformer. So a core has more air gaps. For suppose the air gap between this is, let's consider it as a first plate and let's consider it as a second plate. If the air gap is more, air gap is high, what are the different consequences we are going to face? We need to identify. Okay, we'll go by options. First option is given as reluctance of magnetic path is going to be decreased. So reluctance is nothing but it is a magnetic resistance. Okay, in electrical networks you might have studied resistance parameter. Similar to that, in magnetic circuit resistance is going to be replaced with reluctance. Okay, so if more air gap is there, reluctance will also be high, but the given as decrease. So option A is wrong. This is not correct. Second thing, hysteresis loss. First we need to know what is hysteresis loss. Actually our transformer is going to be excited with the sinusoidal waveform. So for some duration it is going to be positive half cycle, some duration it will be in the negative half cycle. Okay, so whenever we excited the transformer, the phasor diagram will come like this. Okay, if you draw the curve between flux density versus excitation current, okay, it will reach to saturation. So it will reach to saturation. Now the after this it is going to be reduced. Okay, EMF reduced means flux also will reduce, but the reduction path will be like this, and next cycle it will come like this. Okay, so the hysteresis loss is nothing but actually it has to follow the same path, but it is following a different path because of some two properties. One is retentivity, second is coercivity. What is retentivity? Even though our excitation current is 0, still the core is holding some flux. Okay, store is holding some magnetic energy. Okay, this portion you can observe. Even though our magnetization current is 0, okay, the core is holding some magnetic energy. This property is called retentivity. So as per actual it has to come to 0, but it is not coming to 0 because of the property of retentivity. Second thing is, after reaching 0, it is not reaching to 0 immediately, it is going to negative term minus Hc. Okay, minus Hc. The magnetic energy, magnetic field intensity is not 0, even our current is 0. Okay, it is going in negative term. So in order to bring this to 0, we need to apply some more energy. So because of these two properties, we are losing some energy. That means we are losing some amount of electrical energy here. This loss of energy is called hysteresis losses. This loss of energy is called hysteresis losses. Okay, but this is nowhere related to the air gap. Okay, after seeing this concept, you might have understood that it is nowhere related to the air gap. So this is also not correct. Third option is magnetizing current is greatly increased. Okay, greatly increased means if air gap is more, reluctance will be more. When reluctance is more, in order to overcome this, okay, in order to overcome this reluctance, we need to apply more magnetizing current. If air gap is high, reluctance is going to high. In order to get the flux, more flux, we need to give more excitation current or more magnetizing current. Then only our rated flux we can develop in the core. So C will be the correct option. I think Ramesh given correct answer. We will see the last option also. Eddy current is increased. Okay, you might have studied in theory classes. Eddy current is nothing but the losses created due to the circulating currents. Okay, circulating currents in the core. Okay, but the circulation currents will be the inside the core only, not in the air gap. So eddy currents also nowhere related to the air gap. Okay, so our option will be C. If air gaps are more, magnetizing current is going to increase greatly. Those fourth option also not correct. Only our option will be C. So what we need to learn from this question is the basics. That means especially the construction features of a transformer we need to understand. So most of the times the questions will come directly from the conceptual questions like this. That means if you understand the working principle of transformer and different parameters like magnetizing current, eddy current, all this you need to have a basic idea. Then only you can answer the question easily. Okay, is it clear? Okay, we'll move on to the next question. The next question is, when the primary of a transformer is connected to DC supply, what they are asking, the concept is transformer input you are going to give is DC supply. Okay, what is going to happen? First we know that DC supply is a constant voltage irrespective of the time. Okay, it won't vary with the time. This is the first parameter. And frequency for DC supply is equal to 0 Hz. These are the properties of DC supply. Okay, if you give the DC supply to a transformer, we know that transformer this winding is going to provide some reactance and resistance parameters. Okay, since the frequency is 0, if you give the DC voltage here, what will happen? The reactance is going to be 0. The reactance offered by the core is going to be 0 ohms. Only resistance will be there. We know that resistance of a transformer is very, very small. Okay, resistance of the transformer is very, very small. Okay, very, very small. So what will happen? the current flowing through the core will be very high. Okay, current drawn by the core is very high. When the current is increased, the flux developed. Okay, the flux waveform also will be similar to this. The flux waveform also be similar to this, and flux will also get increased. Okay, within a short period of time, flux will reach to the saturation. Okay, flux will reach to the saturation. What is the saturation? That is the maximum point. Okay, maximum point it can reach. Afterwards, the core won't increase the flux. Okay, after reaching saturation, still the current is high, means what will happen? Heat will generate. Heat will generate. Okay, when more heat generated means the insulation will get damaged and there is a chance of burnout. Okay, so our option will be the primary made burnout. Option D. I think Ramesh given correct answer. Answer D. Okay, so we'll see the other options also once. A primary draws small current. No, already discussed here. As reactance is 0, it is the impedance offered by the transformer will be very less. So definitely current will be high. The second is core losses are increased. Okay, core losses is increased means at some point of time, but core losses, what we need to understand is core losses are not depends on the current. Okay, not depends on the current. Not depends on the current. Okay, core losses are not depends on the current. Third is primary leakage reactance is increased. As I already explained, for DC supply frequency is going to be 0. The primary leakage reactance is going to be 0. Okay, this is also not correct. Okay, so we need to look after sometimes what will happen, two options also may be corrected. Okay, two options may be correct. That time we need not get confused. Hope it is clear for all. If you have any doubt, please chat over the comment box. Okay, we'll move on to the next question. Okay, the next question is about a transformer has an efficiency of 85% and works at 100 volt 4 kVA. If the secondary voltage is 200 volt, find the primary current. Okay, the concept is about calculation of the current. What is the concept? Calculation of primary current. Okay, calculation of current. Okay, in general what we need to know is the primary side kVA is equal to U, secondary side kVA, E1 I1 equal to E2 I2. Sometimes some unnecessary data also they will give. What they told, a transformer has an efficiency of 80%. Okay, but that may not be useful for us. Okay, why? Because they given kVA and voltage. So from this we know that if you know the kVA and one of the either voltage or current parameter, other parameter we can calculate very easily. What is the finding terms? What we need to find? Primary current. Okay, primary current we need to find out. I1 we need to find out. So I1 we need to find out means E1 I1 equal to the primary. I told already the kVA will be same for both primary and secondary. It is going to be 4 into 10 cube. What is the E1? E1 is 100 volt. Okay, I1 equal to 4 into 1000. If you cancel out 100 here, I1 is going to be 40 amps. Okay, so our option will be A. Is it clear? So in this question, where we need to be focused is sometimes the data, extra data also they will give to mislead the students. Okay, efficiency may not be required here. Why? Because we can directly calculate the current if you know the kVA and if you know the voltage. Okay, is it clear? Okay, we'll move on to the next question. The next question is about a 20-ton iron core inductor is connected to 100 volt 50 Hz source. The maximum flux density in the core is 1 Weber per meter square. The cross-sectional area of the core is. Okay. So if you see this, what is the concept, on which concept the question is asking? Concept is about transformer design parameters. Transformer design parameters. Okay, what they are asking? Cross sectional area. What are the formulas we can remember? Okay, formula we remembered. As per the given data, if you see, there are number of turns are there, voltage is there, frequency is there, and flux density is there. Okay, we know the EMF formula. E is equal to 4.44 pi ft, where T is the number of turns. Okay, but they given flux density. So we know that flux density is equal to flux per unit area. Okay, from this we can write flux is equal to B into A. If we substitute that in this given formula, we can get 4.44 pi into 4.44 into B into A into F into T. Okay, just look after the given data. What is the given data? Number of turns given as 20. Voltage is given as 100 volts. And frequency is given as 50 Hz. And flux density Bm maximum given as 1 Weber per meter square. What we need to find out? Cross-sectional area, net cross-sectional area we need to find out. Okay, from this formula we can find out as An is equal to E divided by 4.44 into B into F into T. Okay, by substituting the given data we can get as 100 divided by 4.44 into 1 into frequency is 50 and where T is the number of turns given as 20. After doing calculation we can get as 0.0225 meter square. So area of cross section is going to be 0.0225 meter square. Okay, so our option will be C. Is it clear? Okay, so in this question what we need to learn is sometimes the data may be indirect way they might have given. That means we know the formula of induced EMF is pi ft only, but in the given data they given the flux density Bm. So sometimes we have to be interconnect the formulas, different formulas we need to interconnect and we need to solve the question. Okay, that is the lesson we need to learn from this question. Okay, so if you have any doubt, please comment over the chat box. Okay, we'll move on to the next question. The next question is about the no load power factor of transformer is small because. Okay, so first we identify the concept. What is the concept? No load parameters of transformer. No load parameters of transformer. So the question is about no load parameters. So whenever you are getting a question about no load parameters, we need to be remember the phasor diagram of a transformer. Okay, no load condition phasor diagram. Most of the questions will be repeated from the phasor diagram only. Okay, most of the questions will be repeated from the phasor diagram only. So we know the operation principle of a transformer. If you apply voltage, current will flow and flux will generate in the core and it will get induced the EMF E1. The same flux will flow here. Okay, so here E2 will generate. Okay, this all we know about the basic principle of transformer. We'll just draw the no load condition phasor diagram. What we are doing, we are applied some voltage V. Okay, then it is generated flux pi. The flux generated will be always lagging by 90 degrees. Okay, so what are the different no load components we are having? I mu and IW. What is I mu? I mu is the magnetizing component. Magnetizing component. What is IW? Iron loss component. Iron loss component. What it means if we are excited the transformer with the voltage V, what is going to happen? It will draw some current. In whatever the current drawn is going to be for two purpose. First purpose is for generation of flux in the core. Once flux get generated, some amount of flux is going to be wasted in the form of iron losses. Okay, so in order to compensate that iron losses, some more current we need to draw from the source. Okay, that current is called IW. This I mu is responsible for the generation of the flux in the core. Okay, now if you see, the magnitude of I mu is far greater than IW. It is near about 5 to 6 times of IW. Okay, so the component of I mu is more compared to IW. Okay, this is the E1, this is E2. Okay, now the resultant of this I mu and I naught, if you take, it is around like this. It will be like this. That will be the I naught current. So what they are asking? Power factor. What is the power factor? The cos of angle between, what is the power factor of cos of angle between V comma I naught? What is the angle? It is near about 75 degrees. It is near about 75 degrees. Okay, so the no load power factor cos pi naught is near about 70, will be very less, 0.2 to 0.3 lagging. Okay, 0.2 to 0.3 lagging. This is about the no load condition transformer, different parameters. Now we analyze the options. What are the different options given? The first option is iron loss component of I naught is large. Okay, iron loss component. What is iron loss component? IW. So IW is very less. Okay, this option is wrong. Magnetizing component of I naught is large. Okay, so since this I naught magnetizing component is large, our resultant waveform of resultant phasor of I naught is going to be somewhat more lagging by 75, more lagging from the applied voltage. Okay, the major reason for small power factor is magnetic component is very large. We will see the other options also. Magnetic component is small, no. Copper losses are high. At no load conditions, copper losses won't come at all, will come, but very less. Okay, so copper losses are very less at load conditions. So this option also is not correct. Okay, is it clear? So our option will be B. I think the solution is clear for all. If you have any doubt, please chat over the comment box. Okay, we are going to end up the session for today, and we will continue the session tomorrow from 6 a.m. onwards. Okay, please share the link to your friends also. If more participants are there, that will be encouragement to us. Okay, as Govidya, we are providing coaching classes, online and offline coaching classes, and we are providing test series also. Okay, if you have any doubt, if you need personal support also, we are ready to support the students. Okay, if you have any doubts, please comment over the chat box, or you can contact our helpline number as shown in the screen.